Maybe I could just say to the room that you will not be examined on topological dynamics later, except Andras.
Okay. Okay, so yeah, so this solves our problem. So as a corollary, for every definable locally defined template T, it is decidable whether given definable instance I has a solution. We just scan through the monotone invariant assignments and check if any of them is a solution, and this is equivalent to having just any solution.
So the previous argument works with every order graded structure, right? Why did you, okay, is there a reason you chose the order of the rationals? Or?
Well, like, yes, I mean,
You need a dense order or something.
yeah, like, I guess,
I mean,
like,
Because Pestov's theorem doesn't hold if you don't have the rationals there.
but I mean, Pestov's theorem holds for a lot of other structures. I mean,
yeah, so,
why,
yeah, okay, so.
why the rationals?
Yeah, so you can, well, so all of this can be generalized to basically to redux of Ramsey structures. But by using the the generalization of Pestov's theorem.
And your theorem can be proved just using Ramsey's,
Ramsey's.
in fact, they say in the paper. So,
Sure, I mean,
Yeah, so in fact so how we came up with this, we first proved this theorem using just Ramsey theorem, then like we came up with the Pestov, and then with the generalization of Pestov, which makes this much more general.
I mean, somehow more people outside of the area would have heard of Ramsey theorem. Pestov.
yes.
Yeah, that's true. Okay. Okay, so now let me quickly go like once more through this, just using some simple example. So if you fall asleep while I was talking about all this Pestov and invariant things, then you can just quickly have a look at this example. So consider we have this system of linear equations. So well, this system is trivial. Like every equation concerns different variables. Of course, this is decidable, but well, this is. Yeah, but there can be more difficult examples. So we have this system, this infinite system of linear equations. So here we have infinitely many variables of this system, and of course we have infinitely many different possible assignments. So to check whether this system has a solution, we would potentially have to scan through all infinitely many different assignments. So now we want to clear this mess. So we consider just invariant assignments. So if we consider invariant assignments, then all those variables are in some sense the same. So we have just two of them, and none of them is a solution to this system. And yeah, we know that the system has a solution. Invariant solution don't help. So we introduce the order on atoms. So let's say that in this order, those atoms that I mentioned here are ordered like this. So now those variables, if we consider all permutations, then those variables are all the same. If we consider monotone permutations, then those are different than those, because here A and C are, A is smaller than C, so the pairs are in this order, and here the indexed pairs are in this order, A and E. A is bigger, well, E and A, okay, maybe I missed something. But it's supposed to be, here we have smaller and here we have bigger. Okay, but then we get two kinds of variables. So now when we consider monotone invariant solutions, then we have two more. So of course, the previous ones are still monotone invariant, but we have two more. And among those, we can find a solution to this instance. So the picture looks like this. Okay, so this was the decidability of the locally finite space piece. So now let me tell you a few words about complexity. So in the classical constraint satisfaction problem, like what people considered, let's say, at the beginning, is they considered finite templates and finite CSP instances over those templates. And they were asking, like the main goal of research was to characterize characterize those CSPs which are solvable in p-time. Characterize those templates for which CSP over this template is solvable in p-time. So now let us try to do the same. So we modify our problem. We only consider, so now we will only consider, still we have a definable locally finite template, but we only consider finite CSP instances over this template. And we want to know whether those characterizations that we have for the classical CSP, whether those can be generalized to our frameworks, so to locally finite templates. Okay, so how does those, how do they look like, those characterizations for CSP? So for example, there's a wide class of templates solvable in p-time. Those are templates, so-called templates of bounded width. And those are templates for which, for which the CSP can be solved using data log, for example. Or there is some canonical algorithm which is called ToCAI consistency that you can use to solve those CSPs. And there's a famous theorem which is kind of it follows from results by Zadori and Bacco and Koji, which says that a finite template T has bounded width, meaning solvable by data log, if and only if some particular instance that we can construct from this template over this template has a solution. And this instance, let me just mention that this instance characterizes some algebraic properties of this template. Okay, and this is kind of an easy corollary from the result of Zadori, Bacco, and Koji, which says that, and this also uses compactness. So it says that we can basically use the same characterization. So locally finite template T has bounded width if and only if this instance that we can describe over this template T has a solution. But what is maybe more interesting is that this instance is a definable instance which is computable from T, which gave us, so for finite CSP, it's obvious that the characterization that I mentioned is an effective characterization, because we have a finite template and a finite instance. So here, like, from this, it doesn't follow that this is an effective characterization, but if we use this decidability result that I presented to you a few minutes before, then indeed we get an effective characterization of locally finite templates of bounded width. And the similar results can be, like, many of classical results from constraints like from classical CSP can be generalized to locally finite CSPs. In particular, if the algebraic dichotomy conjecture is true for CSPs, then it will be true for locally finite CSPs. Okay, so let's move to the last point. So descriptive complexity. So how did we use all this machinery to how can we relate all this machinery to descriptive complexity? So descriptive complexity theory is a line of research that tries to identify logics which are equi-expressive with some known complexity classes over finite relational structures. So an example of a theorem from descriptive complexity, like a well-known tagging theorem, which says that existential second-order logic captures NP over finite structures. So every property decidable in NP can be defined by an existential second-order formula, and every such formula defines an NP property. And then, we can say that the central open question in this area is whether there exists a reasonable logic for p-time, so quest for logic for p-time. And for some time, there were like two candidates for such a logic considered. So there was existential, least fixed point logic, and then least fixed point logic with counting. So least fixed point logic is the extension of first order logic with by a fixed point operator, and then we add the power of counting, which is least fixed point logic with counting. So the first results were promising, so Immermann and Barney proved that LFP captures p-time over linearly ordered structure. So if you have a structure which additionally have a linear order on the set of vertices, then indeed LFP equals p-time over those. But then it turned out, like a construction by Seyfried and Immermann, that LFP plus C does not capture p-time over all structures. So now, how does this correspond to the things that I've been talking about before? So, I hope that you remember linearly p-bar structures. So we have a graph covered with subgraphs, and we have equipped with a linear order on the set of those subgraphs. And we talked about this isomorphism of linearly p-bar structures, and I told you that every instance of this problem, isomorphism of linearly p-bar structure, is over a locally finite template, which depends on the structure P. So now, those results that I presented before can be stated in the language of linearly p-bar structures, meaning the first theorem, the theorem of Immermann-Varney, can be rephrased to say that LFP equals p-time over linearly p-bar structures, where the patches look like this, so the patches are just edges. So so the linearly p-bar structure, when the patch is just an edge, are formally structures with linear order on the set of edges, and the Immermann-Varney theorem talks about structures with the linear order on the vertices, but of course, like, this is almost no difference. It makes almost no difference. And then there is another theorem. If we take P to be some graph with 6 vertices, and in fact it can be just a sum of 2 triangles, then we can show that LFP does not equal p-time over linearly p-bar structures, where this is when the patch looks like this.
Is this LFP just LFP or LFP plus counting?
Yes, so sorry, I didn't make this remark. So over linearly p-bar structures, because they have, like, the patches always have fixed size, so counting does not add any power. So LFP plus C equals LFP over linearly p-bar structures. So this also says that LFP plus C does not equal p-time over linearly p-bar structures. Okay. And then we can, so then, like, using all this machinery, we came up with a common generalization of those two theorems. So the following conditions are equivalent. LFP captures p-time over linearly p-bar structures, if and only if this template that I introduced before, this locally finite template that we can construct from P, has bounded width. And moreover, as I told you, like, this checking whether some template has bounded width is effective. So this template can be computed from P, and we can decide whether it has bounded width. Okay. Thank you very much.
Have any questions for Joanna?
So I was not able to follow the last results very well, but for the first part of your talk, it looked like you were doing a development of nominal logic, sort of in the mathematical universe. So you're using equivariance and so on. And it looked like it was an attempt to restore equivariance.
Yeah.
But then you decided that sort of the abstraction imposed by nominal logic, like all atoms are born equal, is not suitable, right? So you went for a refinement of the nominal logic with order. Is this?
Yeah. So I think that what we are doing in Warsaw is so we are considering like nominal sets and like different nominal things, and we are considering like what happens if instead of considering atoms with just with the equality relation, what happens if we consider like similar objects but defined over more richer structures. So in particular with atoms with order or random graphs or things like this. So yeah,
Okay,
this
so
is
this
kind
was
of-
actually my question. So what kind of structures are you considering
What kind of-
or
so-
find useful besides order?
Well, so we consider those like objects like this, for example, definable sets for different structures, but for for some structures those objects are well behaved, like for example for atoms with equality or atoms with inequality, or rational numbers with inequality. For some structures, like for example natural numbers with successor or natural numbers with order, those are very badly behaved. So and the general picture is that everything kind of follows from model theory. So like for homogeneous structures, things are well behaved, and for non-homogeneous structures, you get some strange phenomena that are also. So we are also considering like computation over atoms. So it also if we define some computational models with over atoms, then they are well behaved. Like for example, emptiness is decidable if the atoms are homogeneous, and many things become quickly undecidable if the structures are not well behaved, so not homogeneous.
So yes, it sounds like an interesting connection with the theory of parametricity in programming, because there you also have this notion of the meta theory of programs is well behaved so long as the programs are not going to do non-uniform things on types. So this looks like sort of a notion of parametricity that is restricted to certain kinds. Parametricity with respect to bijections, parametricity with respect to monotonic functions, and so on.
David?
Yeah, I was wondering if what would extend to graph structures with directed edges. I mean, I was thinking maybe a correlate problem with the adjacency conditions relaxed in certain directions. But maybe that's not a constraint satisfaction problem. It wouldn't be a series of linear equations.
I think that I would have to get a definition from this.
I mean, the inputs are going to be symmetric somehow because they've got to be preserved by the automorphism. So the inputs can't be directed somehow.
Also, the linear equations, I guess, aren't necessarily bidirectional.
Yes, it's commutative.
Yeah.
You have some problems if you try to add directedness to it, right? Because the input structure.
Directed graphs, for example.
Yeah, I imagine that some cases directed, defined some cases.
You can imagine, like, for example,
Directed
if
three
you
cycles
have-
or something.
Well, then you have to. Yeah. So, for example, if you have order, then it should be easy. Like, for example, you can have just variables indexed with atoms with order and directed edge from XA to XB if A is smaller than B.
Yeah.
So I don't know, like if you have a quality, then you'd have to think about some set of indices.
But you can't express that in a quality, you need something else.
Yeah, this you can. That's.
And with equality, you always have this symmetry. So
Yeah, you could have you could have maybe different kind of different because here in all the examples that I gave the variables were they form one orbit under the action of permutations, but we can take two orbits and then have some directed edges between those. So if you have an edge in if you have just one orbit of vertices. And if you have an edge, then of course you have it goes both sides. But if you have two orbits of vertices, then there should be no problem with defining them.
but in something that's equality definable, how do you have two orbits of vertices?
You can just have it's no problem. You can just take disjoint. So yeah, this is those
Orbits of pairs,
subtleties. So the subtleties with this. What does it mean to what does a definable set mean? But it's it's no problem. this should capture taking two different orbits of, for example, X, AB, and Y, AB, like,
Orbits of pairs.
yes.
Yes, okay, of course you can have multiple
Yeah, yeah,
orbits
yeah.
of pairs.
Well, you can have one orbit of pairs and one orbit of, like, triples or
Yeah.
whatever. But yeah, if you have more orbits of variables, then there should be no problem.
So this might be a separate question. So you talk about velocity, and I'm just wondering. So I mean, can you like get some kind of like I don't know p space x pressure time, like those velocity outbounds for certain, let's say, templates or.
So
Because
well, it depends on the kind of, so there are different. So we considered different kind, like, well, there's this most general framework where you have definable instances and definable templates, but now you can consider finite instances over definable templates, and this is in NP because it's a classical thing. So then we also considered, well, I think that we didn't really think much about the complexity of the most general case, but then you have the complexity, so you can think about definable instances over finite templates. So, like the first two examples, you had infinitely many variables, but finitely many values, so colors or 0, 1. Yeah. So then we kind of we did consider complexity, and it turns out that if you have a classical CSP problem, so finite instances over finite templates, and this CSP is, for example, in log space, then the infinite instances, considering infinite instances over the same template, gives you an exponential blow-up. So it will be, but maybe this I can maybe explain it later on. So yeah, so in general, if the problem for finite instances has some complexity, then and you keep the same template, then this problem, if you consider all definable instances, will be like there will be exactly an exponential blow up in the complexity.
Okay, I guess that's a good time to wrap up. Maybe we'll go for coffee or something. If anyone wants to join, talk about this. We thank Joanna once more.